Thanks. Got it. All right, yes, thanks everyone for attending today, and a special thanks to Ephraim for the invitation and the kind introduction. It feels great to be back with you all in Toronto, if only virtually. And I'm eager to share with you all what I've been up to for the last 6 months or so, and what I'll hopefully be, able to be showing experimentally in the next couple of years. Okay, so today I'll be telling you about a new proposal fresh out on the archive a few weeks ago for a new architecture for quantum computing based on trapped ions or Rydberg atoms inside an optical cavity. And I'll also say just a little bit about my very preliminary work towards a Rydberg implementation of that architecture in the lab. So I should start by acknowledging that everything I'll be telling you about today is work done in close collaboration with members of the Research Group at MIT, and in particular with Josh Ramet, if you can see my mouse, on the theory side, and with Alyssa Rudelis on the experimental front. So before I dive into the details of the proposal, let me make just a few introductory remarks, starting with what is a quantum computer. I'm sure you all are by now experts in this as well, but let me start by saying very simply that a quantum computer is a type of computer that has the ability of all quantum systems to be in a superposition of many states. And this capability makes a quantum computer, like any large quantum system, potentially very, very hard to efficiently simulate. These, oh wait, hold on, sorry. Oof, having some trouble here. Okay, hard to simulate. However, since the mid-90s, it's also been known that at least theoretically, a quantum computer will be much faster at solving certain types of problems, such as prime factorization, and that might be useful in all sorts of real-world applications. These findings have spurred on a global technological race to build a useful quantum computer with, as you're all aware, large public and private investments in competing approaches. And so far, it seems as if the investments have paid off. At the moment, small-scale quantum computers have been built on a variety of hardware platforms, including trapped ions, neutral atoms, superconducting circuits, and photonics. And in most or all of these platforms, all of the basic primitives required for quantum computing, the elementary operations, so to speak, have been demonstrated. Okay, great. So that's fantastic, right? But what's the next step? So in the short term, the challenge will be to scale up the size of existing devices to the so-called noisy intermediate scale, coined NISC, where they will have hopefully narrowly defined uses despite rampant errors. Beyond the NISC error, however, realizing error correction and building fault-tolerant quantum computers large enough to solve problems that are intractable for classical supercomputers remains both an enormous scientific and engineering challenge and, the holy grail of quantum information science. So regardless of whether you're thinking near or far term, a major challenge for any quantum computing architecture is scaling up the number of qubits while maintaining a high degree of connectivity. And by connectivity, I really just mean, I want all of the qubits in my computer to be able to talk to each other directly. So why is connectivity so important? Well, when you use a platform that's constrained to local gates, perhaps only nearest neighbor gates, for example, far separated regions of these large and noisy devices cannot be entangled, because this would require a long chain of swaps all the way across the device. with a success probability that scales exponentially badly. And effectively, this limits the number of qubits that can be simultaneously pulled in to computation. In other words, it limits the effective size of the Hilbert space that can be explored by the device. In addition, according to what the quantum algorithm folks tell me, many near-term NISQ applications, such as simulations of quantum gravity or qubit-based encodings of the fermionic molecular Hamiltonian, all require a high degree of non-locality. And so it's not just a sort of long-term goal, but if we want to be able to do interesting NISQ-type applications, connectivity is a really important metric to be thinking about. Beyond the NISQ era, thinking longer term, full connectivity is also very favorable for quantum error correction, enabling codes which have better error thresholds and which have higher encoding efficiencies, require fewer physical qubits per logical qubit, and offer better suppression of errors. And I couldn't help including this archive. So just today on the archive, there was a breakthrough in low overhead quantum LDPC codes, low density parity check codes, which require a lot of connectivity, but have extremely favorable properties. This is a really exciting time for error correction, and a lot of the most favorable error correcting schemes trade on having a large amount of connectivity between qubits. Okay, so connectivity is great. That's what we all want. Unfortunately, connectivity inherently conflicts with scalability in most of the existing architectures, simply because having both requires either a very high dimensional topology or infinite range interactions. And neither of those are very naturally available in the existing platforms. So for example, Rydberg atom arrays, a really promising hardware platform that are very scalable, right? The largest Rydberg array right now is about 250 qubits, but they're at least so far limited to nearest neighbor gates. So I have a double asterisk there because I should add that there have been some very promising results recently involving mid-circuit reconfiguration of Rydberg atom arrays. So there's exciting stuff going on there, but that's kind of working parallel. So another really promising hardware platform for quantum computing is superconducting circuits, which are also very scalable, but are also only natively able to support few neighbor interactions. So an interesting contrast would be trapped ion quantum computing, which are any-to-any connected. However, so that's the largest any-to-any connected system that's available to date. And they've been large as few as, they've been scaled up to a few tens of qubits, maybe 20 qubits. However, what we've seen is that increasing the qubit count further results in severely degraded gate fidelities. And there's been heroic efforts to sort of get past this limit, but it looks like a pretty challenging barrier to pass. So there are various approaches to interconnecting, two or more trapped ion quantum computers. They're being pursued both looking at photonic interconnects and ion shuttling, and both have some promising features, but both are expected to remain on the order of hundreds of times slower than the local Coulomb gates, which imposes an unfortunate bottleneck on larger devices and their operation rates, and it's especially going to be challenging to combine with error correction. Also, these methods typically face other engineering challenges, including designing very fast, very low loss optical cross-connect switches at ion-compatible wavelengths, combating excessive heating, or trying to realize two-dimensional shuttling geometries, which are currently, some people are working on but haven't fully realized yet. But I don't want to be too critical here. I actually would probably say that it's very likely long-term that photonic interconnects will eventually be required to scale above a certain size. But I think it's fair to say that they'll probably always be slower and noisier than the local, QOAMO or Rydberg operations. And so in parallel to these, very important ongoing efforts to improve existing hardware, there's a lot of interest in new approaches to making, fully connected systems as large as possible. And that's sort of the motivation for this paper and my work. Okay, so that brings us to this proposal that I was telling you about, was put out in the archive a few weeks ago. So what we proposed is a new architecture for quantum computing, which takes small, high fidelity local quantum processes, which could be chains of trapped ions, or it could be, small pairs or collections of Rydberg atoms, and it places them inside an optical cavity and connects them using heralded single photon transfers. So it's possible to give this entire talk in a hardware agnostic way, where I talk about local processors and so on. But in my opinion, it's much more confusing. And so I'm gonna, for most of the talk, focus on just the Rydberg implementation of the architecture.
Josiah,
go ahead.
Can I stop you for 1 second? So when you started off by talking about NISC, and then you went on to larger fault-tolerant systems. I'm kind of wondering, roughly, if you can give an idea of what kind of sizes you're looking at. Just totally. So I have a picture in my head.
Yeah, no, great. So this actually leads right into the appeal of our architecture is slightly different for the two platforms. If we talk about Rydberg arrays are already fairly scalable. The largest systems are hundreds of qubits, and probably a hard upper limit on the size of a Rydberg array is about 10,000 qubits. So scalability isn't the problem, it's connectivity. And the advantage of our architecture for Rydberg arrays is that it would allow 1,000 or maybe a few thousand, up to 10,000 Rydberg atoms to be fully connected. So we're talking about a NISC device with maybe 10,000 any-to-any connected qubits. On the trapped ion front, trapped ion chains are already any-to-any connected, but the chains are not able to be made much larger than about 20 qubits without big degradation in gate fidelities. And so the advantage of our architecture for trapped ion computing is that we show that you can connect up to about 20 chains containing about 500 ions with microsecond gate speeds and fidelities limited by the local Coulomb operations and readout inside a single cavity. So it's a slightly smaller number for trapped ions, but still about an order-ish, order and a half of magnitude increase in the largest possible system size that's still fully connected without giving up, connection speeds or fidelities. Does that answer that question for you, Aaron?
Yeah, it does. But just another question. So for the Rydberg, you are talking about gate, quantum computation, or is it more like quantum simulation kind of stuff?
Yeah, digital.
Okay.
Digital simulation, yeah. For, in the NISC era, at least, yeah.
Okay.
Yeah, so we're going to require every single qubit have individual control along with individual any-to-any 2-qubit gates. Okay, so hopefully you're at least intrigued. So now let me try to tell you about how this is all going to work. With a sincere apology to any of the ion folks in the audience, for the sake of clarity, I'm going to focus on the Rydberg implementation. In the paper, we talk a lot about the trapped ion implementation as well. We're really excited about it, but it's hard to explain them in parallel. So I'm just going to focus on the Rydberg implementation here. Okay, so the first thing I should say, though, is that there are, and anyone in the audience who's been here for a long time will know that this is not the first proposal for doing quantum computing with atoms inside cavities. In fact, some of the earliest proposals for how to implement a quantum gate between two atoms actually are from the 90s, and they involved photon transfers inside a cavity. So no Rydberg atoms, we're just using the cavity to mediate two atoms interacting. And the basic idea of these proposals was to induce, so I've kind of got a sequence of 3 diagrams here, which you should kind of read sequentially going down. You've got 2 atoms in the cavity. They're both 3-level atoms. And the idea is to induce like the left atom, the control atom, to emit a photon into the cavity only if that atom is in a particular state. And then if that atom is in that particular state, it emits that photon into the cavity, and then we can induce a second atom to absorb that photon and undergo a state change only if it's in a particular state. So if the control atom is in the wrong state, nothing happens. But if it is in the right state, the target atom, will have its state flipped. And this is sort of, rough at this stage, but you can see we kind of have the ingredients we need for, a conditional logic gate between 2, potentially very far apart qubits mediated over long range by the cavity. So that's going to be, these are the kinds of ideas that inspired our proposal, but our proposal is going to be pointedly different than these. And the reason is that all of these ideas have like a big problem. And the problem is that the quantum information has to travel through the cavity as a photon. And there is always a chance that the photon will get lost because it leaks out of the cavity or because the atom, scatters a photon to the side during the absorption or emission process. And if that happens, that photon will contain information about which state the atom was in, and that'll decohere your whole quantum computer. How likely is this to happen? Well, to prevent it, you basically need a perfect cavity. And people have spent a lot of time thinking about this, and what they basically concluded is that it's just too hard to make cavities good enough to make this sort of gate work under, realistic error thresholds. You would need something like, you just need cavities that are so far beyond what's available in terms of optical qualities that people have largely abandoned this as an approach. I don't know if you can see, I've added these little decays from the excited state and out of the cavity. Okay, so how do we get around this problem? So where the original proposals involved qubits doing gates directly through the cavity, and thus requiring the error, the chance of a photon being lost to be very, very small, we have come up with a very, very different approach. So let's take a look at this diagram here. So we have got in this diagram all the important elements of our architecture. So we've got memory qubits in red, which are where all of the quantum information for our computation is going to be stored. And crucially, these memory qubits do not interact with the cavity at all. In fact, we even suggest, because it's a theory paper, we suggest making the memory qubits a totally different species to be good and sure that they don't ever interact with the lossy cavity. What does interact with the cavity is the communication qubits in blue here. And finally, as you can see, the memory and communication qubits, the memory and communication qubits are arranged in pairs so that each memory qubit can do a Rydberg gate with its partner communication qubit. And those are the only local gates that we're going to be thinking about. And we're going to, to make sort of help with the language, I'm going to refer to like a pair here as a node. So that's kind of like one local node. So our approach to realizing, a long range 2-qubit CNOT gate involves 2 steps. First, we're going to create a Bell state between the communication qubits at nodes A and B by passing a photon from A to B via the lossy cavity. If we design our transfer through the cavity right, we can measure that the communication qubit at node B is not in a certain state without destroying the entanglement. And that will herald successful establishment of this entangled state and leave the communication qubits at A and B in a Bell state. Once we have prepared this Bell pair between A and B, we can then do local CNOTs using Rydberg interactions between our communication and memory qubits at nodes A. And at node B. Then we read out, we do measurements of the state of the communication qubits at A and B. And conditioned on those outcomes, we do some single qubit gates on the memory qubits, and that enacts a teleported C0 gate between the memory qubits at A and B. So the idea here is that if you can herald a Bell state with high fidelity between communication qubits A and B, then you can do a teleported gate with only local operations and readout. And the fidelity of your teleported gate will be limited by the fidelity of those local operations and the fidelity of your heralding, and not the quality of the cavity. All right. So hopefully that makes sense. And now let me explain how the heralding process is going to work, because that's going to be, basically the key to this whole thing. So here's like a basic idea of how heralding Bell state creation might work. It's sort of a simplified version. So you've got your two communication qubits, A and B, which I have just represented as two-level atoms here. And to entangle them, we'll just start with the communication qubit A in the upper state and the communication qubit B in the lower state. And we will then, apply individual fields and first induce communication qubit A to release a photon into the cavity, which now in step 2 is absorbed by communication qubit B, exciting it. If this process fails because the photon leaks out of the cavity before it's absorbed by B or something goes wrong, then both atoms just stay in the ground state, both atoms end up in the ground state with B having never left it. We can then just measure the occupation of the lower state in B. And if the atom is still there, then we know the transfer failed. And we just repump and try again. But if the lower state of the second atom is empty, that will herald the successful transfer of the photon from the first atom to the second atom. And then if that's designed properly, that'll also herald entanglement of the two atoms.
Josiah,
yeah.
Can you explain how, so two questions. One is, how is information encoded here? Because
sure,
it's not encoded in these two levels. And then the other question is, what about atom C that's in the center, C, D, E, F that are between A and B? I'm kind of imagining that you're shelving them onto the excited state, but.
Totally. So I've not shown you the full level scheme that I need both for encoding and for shelving yet. I will soon. That's like the next slide. So you're right. So I haven't shown you how to really create an entangled state yet. I've just shown you how to check whether a transfer through the cavity succeeded or not. But I promise that's the next thing.
Sorry, I'll ask another question, and maybe
sure.
you're going to answer this. But when I mean, you need to detect a photon from B, right? At the
no,
last
I just
step.
need to measure. I just need to measure that B is not in the ground state.
Okay. Sure. Okay,
so I can do it however I want.
Yeah. Okay.
And I'll talk about how the best way to do that. Okay. So yeah, so far this is not in its full glory, but I will in a second show you a more detailed and
one clarifying question is,
yeah, go ahead.
Can you say measuring heralding on empty ground state, is that the same as heralding on an excited state, or am I confused?
So in a two-level atom, yeah.
Okay. All right.
Okay, I also have a question. So we say measuring empty B ground state heralds successful entanglement. So how do we measure a state of B without disturbing the entangled state?
Totally. So what's going to happen is that there will not be just a single excited state, but there will be a pair of them, and you'll have a superposition in the pair of excited states. And then if you measure that you're not in the ground state, that doesn't disturb your superposition in the two excited states.
So 0, 0, AB plus 1, 1 AB means So yeah, I thought it meant 2 of them are at ground state plus 2 of them are at excited state. Then that's not the
Okay,
case.
let me just jump ahead to like the next slide,
Okay.
and I'll show you the full level scheme and how this is really going to work, because you're asking the right questions, and yeah, let me just answer them with slides. So the main thing to describe, right, is how do we actually use the cavity to distribute entanglement and in this heralded way check that we've succeeded. There's a tiny bit of math here, but you're all asking for it, so I don't even feel bad about showing it to you. It's only a few slides anyway. Okay, so first the level scheme. So here's the level scheme for the communication qubits in our proposal. We've got 2 long-lived logical states for our qubit in the hyperfine levels. And we're going to have a pair of long-lived Rydberg states, which we'll call our operation states. And one of the operation states, R naught, and one of the logical states, 0, are going to be linked by a 2-photon transition, where one leg of that transition is the cavity. So if this was rubidium, like in our proposal, this intermediate state would be the 5p3/2, maybe x equals 4 state. And these would be highline Rydberg states with when this like omega I beam would be a 480 laser, and the cavity would be tuned to about 780 nanometers. So our protocol starts in the following state right here. So the control is in a superposition of R0 and R1, and the second communication qubit is just in state B, and the environment has no photons. Okay, so next a photon is transferred through the cavity from qubit A to qubit B, conditioned on, qubit A having been in R0. So only, 1/2 of the superposition is having anything happen to it. So this transfer is done using Raman pulses or stirrup, and it requires individual addressing of the 2 communication qubits. And I should add that every other communication qubit in the cavity needs to be shelved in logical state 1 or some other shelving state while this is happening. Another option would just be to take your atoms and move them, about a micron, such that they're no longer at the antinodes of the cavity, and then don't talk to the cavity anymore. In general, I'll say it's not very hard to make atoms not talk to your cavity. Experimentally, the challenging thing is to make your atoms talk to the cavity. So we have lots of ways to, take communication qubits out. Okay, so this transfer can fail, right? Due to scattering or cavity loss, and in that case, both qubits are left in the ground state, and the cavity is left empty. So this is the state I get after that first transfer. You can see, so R1 0 vacuum, that half of superposition just stays unaffected, and the R0 0 vacuum turns into, R0 on qubit A turns into 0 on qubit A, and 0 on qubit B turns into R0 on qubit B, plus this, beta amplitude for loss. And that loss would be basically a photon in some mode flying away from the cavity with information, and qubit A and qubit B in some combination of ground states, depending on, what all the decay channels are, whether E can decay to 0 or to 1, right? And the only thing that's important for our scheme is that E cannot decay upwards. So E isn't going to be allowed to decay into a Rydberg state. So loss always involves, a spontaneous emission event of some kind where the atoms are all left in their ground manifold. Okay, so if you look at the state, you can see it's already some kind of entangled state, right? You can't factorize this easily, but it's not a very nice one, mostly because if beta isn't 0, then it's not like an even state. There's more amplitude to be in R1 0 than there is to be in 0 R0. Oops, sorry. Here's our state again at the top. And this is an entangled state, but it is a lopsided one. So we're going to want to symmetrize our losses by repeating the transfer so that now like both halves of our superposition will have gone through the cavity once and we'll have a Bell state that's symmetric. So to do this repeated transfer, we have to do some swaps. So conceptually on both qubits, we swap the operation states. R0 and R1, we just flip them. And then on qubit A, we also swap the ground states. And that's important because you'll remember that on qubit A, if you look at the state, qubit A is in 0. So we do a swap, and now qubit A is in 1, right? And then R0 swaps to R1 on qubit B. R1 swap to R0 on qubit A. And we don't do anything to the logical states on qubit B. So we just do these swaps, right? That'll involve, individual Raman beams addressing the different atoms. Okay, after the swaps, we can then just repeat the Raman or stirrup transfer. And as long as we do these two transfers close enough together, the idea is that the probability amplitude for failure will be roughly the same. And as a result, we'll have a state that looks like this, the very bottom here. So you can see that if you compare like this state to the final state, this first part hasn't changed at all. And it's just the second half of the superposition that's now had the swap where R0 went to 0 and 0 went to R0, so it's kind of a transfer. And there was some, loss that happened, which created a, loss prime state, which is a photon with a new K vector flying off and all the atoms in the ground manifold. And all that we need is for all the loss states to involve, both qubits A and B being in the ground state, and for those amplitudes to be the same. And now we're just going to measure whether atom B is in the ground state. And that is going to project us into either loss with amplitude beta squared, or it's going to project us into a Bell state with amplitude alpha squared. Okay, I'll just maybe stop and ask if there's any questions about that, because that's like the core of the idea.
Yeah,
everything else is going to be experimental details.
Yeah. Why are you justified in having a coherent superposition of the loss mode and the other stuff? Why doesn't it become a mixed state?
So if we like traced over it, it would be a mixed state.
Mm-hmm.
But we can just measure, is the atom in the, is atom B in the ground state, and like project onto that. If it is onto that state. Yeah, I mean, basically under this measurement, we just project out all those cases. Or, if, yeah, and maybe I'm not sure if there's anything else I would say about that.
Okay, I think I see what you're saying.
So,
Josiah?
Yeah.
I also have a question concerning this, and maybe a bit of like related to Noah's point. There's these levels are not degenerate, right? So like if you have any sort of like timing delay, you're gonna have, right? And is there a reason? I'm not too familiar with the level schemes of Rydberg, but like, is there any reason why you don't go to like a degenerate space for the two like upper levels and also the shelving level?
Yeah, sorry. So I think, 0 and 1 will be gigahertz apart because that'll be set by the hyperfine splitting of rubidium. And those are extremely long-lived. Those we're like not worried about. The Rydberg levels will also be gigahertz apart if we, pick ones that are around n equals 70. Those have a lifetime that is not as long as the hyperfine states. And so maybe to come back to Noah's question, if we waited too long, we would get some dephasing, and then, it would be too late for us to do this measurement. So if our measurement of, the atom being in the ground state or not of qubit B took way too long, this wouldn't work. we need to be able to maintain this coherence, while we're doing the measurement. But as we'll show, we can do it in a short window of time compared to the Rydberg lifetime, and that's like kind of what allows us to do this heralding on coherent superposition.
And you're also affected by a Stark shift here, right? Am I correct?
Say that again?
Are you affected by Stark shifts here?
Yeah, so if something happened that like mixed our Rydberg levels, then that would be completely decohering our Bell state, yeah.
Josiah, I've got a question that's more about your architectural philosophy than about the physics details. I don't know if you'd rather I wait until the end and you go through the physics now, or if you want this interlude now.
Oh, let's go.
I'm just curious whether you've really thought about the trade-offs and whether it's obvious that all-to-all connectivity is the best. I mean, obviously, ceteris paribus, it would be, but there are costs. And in particular, I don't feel like you've been explicit about what the resources required are to resolve each individual node inside this cavity. And I imagine that, it'll require some gradient or frequency control or what have you that might mean that it would slow down the processing. So I wonder if you've thought about whether there are intermediate regimes where you don't have full addressability, but you get more speed in return or something like that.
Do you mind if I keep going? Because I kind of will come to some of these questions.
Excellent.
And then let's come back to it after, because these are really interesting questions.
Okay, but
So
let me ask maybe
details. Yeah.
a more specific one first, because you are talking about scalability and you pointed out that ions were currently at the stage of tens unless you shuttle from far away, whereas with Rydbergs, we can make much larger arrays. You quote 10,000 or 100,000. But that's in part because we have multidimensional arrays, and it looks like you're moving us back to one-dimensional arrays for this geometry. So doesn't that actually bring us back to 100 or a few hundred sites for the Rydberg array?
So we think we can fit about 1,500 Rydberg pairs inside our cavity if we have the right packing. So it's a small hit, like a factor of 5 or something maybe.
Packing. So it wouldn't be a purely one-dimensional array. You'd have a multi-dimensional array within the cavity mode.
Yeah, what's going on is the cavity mode is like 10 microns thick. And so we can have a few pairs that are packed into that rather than being purely 1D like my cartoons have been.
And have full addressability. Okay, good. I'm looking forward to hearing the rest.
Okay, so let's talk about.
Can I ask one more question? Sorry, Josiah. I'm just trying to understand this. Not in the ground state measurement still, and which of these does one of these equations show after you've done this measurement, or
no. So I'm just showing you this bottom equation and saying that all of these like loss states involve qubit B in the ground state and a photon in like some direction. That's why there's a prime, right? It's like one photon one direction, one photon different direction. But if we check and no atom, and if we check and qubit B is not in the ground state, then that just collapses us to the remaining part of the superposition with probability, and that happens with probability alpha squared.
But it seems like if it's not in the, okay. So this measurement has to check. So you really just want to know, is it in the ground state or not? You don't want to know which state it's in.
Right. So like it needs to be able to be in some superposition of R0 and R1. And then we just check, is it in the ground manifold? If the answer is yes, then we know it's not a superposition. We also collapse it and we don't care because we're just going to try again. But if it is not in the ground state, then we know that we succeeded because all of our failure modes leave it in the ground state.
Are you going to talk about how you do that measurement or?
Yeah.
Okay, cool.
All right, so in like my 15 minutes I still have, let me see if I can get all these experimental details in. All right, so experimental implementation. We suggest using rubidium atoms for communications because we love rubidium. mainly because it's got a very convenient transition at 780, where high finesse cavities aren't easily available, and because it has nice hyperfine ground states that are very long-lived. For the memory qubits, we actually propose using ytterbium because ytterbium has magnetically insensitive metastable nuclear spin states, which have even longer lifetimes, like 25 seconds or something. And those long-lived states can access Rydberg states with only a single photon transition. So these are appealing properties, but if that's intimidating, you also just use rubidium 85. The most important thing is that it not be the same wavelength. For the cavity, we choose a cavity with a length of about 2 centimeters so that Rydberg atoms can always be order 1 centimeter away from any dielectric surfaces in order to keep their lifetimes good. And we're going to have a finesse of about 140,000, which means the ring down time is about 3 microseconds. And remember that time, that'll be important. We'll have a Gaussian wave of about 10 microns, which means the atom cavity coupling will be comparable to the excited state spontaneous decay rate. And with these kinds of parameters, we've simulated stirrup transfer efficiencies and found that with about 70% efficiency, we can do a transfer from qubit A to qubit B in about 2 microseconds. Now, creating a Bell state requires 2 transfers, right, to symmetrize the 2 halves of the state. And we only have a 70% chance of success. So it ends up taking us about 6 microseconds to establish this Bell pair, assuming that state readout is instantaneous, right? Just in terms of the cavity transfers, though, it takes about 6 microseconds. Okay, so teleporter gate requires 1 Bell pair along with local operations of state readout. And the state readout is pretty important, right? And as Noah was right to ask, how do we do that? So this is actually a tricky thing for Rydberg atoms because non-destructive fluorescence imaging of dipole trap neutral atoms typically takes milliseconds, very, very slow in order to not basically blast them out of the trap. That's kind of a no-go for us because we don't want to wait milliseconds to see if our entanglement succeeded if it's going to fail half the time, However, the cavity itself can enable fast serial state readout. Basically, the presence of an atom in the cavity modifies the index of refraction of the cavity, shifting the resonance condition. So you can see here, I've got saw this picture on the internet of a pretty famous avoided crossing experiment where the cavity's transmission strongly depends on presence or absence of an atom in the cavity. And what we've worked out is that we can measure transmission through the cavity and reveal a state of an atom in about 1 ring down time. So using the cavity, we can do in about 3 microseconds, a measurement of is it in this state or not. So that adds a little bit to our time, but we're still talking, maybe 10-ish microseconds to establish this Bell state. Okay, as Ethan was asking, how many atoms can we fit inside the cavity? Well, our double-sided Rayleigh range is about 1 millimeter, and our beam waist is about 10 microns. So taking sort of standard distances under which you have like high Rydberg gate fidelities and thinking about packing things cleverly, we think we can fit approximately 1,000 pairs inside that double-sided Rayleigh range. So, every pair is at least, about 1 centimeter from the walls of the cavity. And they all have at least like 60% coupling to the cavity still. So that was kind of our cutoff. So if you have a probabilistic loading procedure, right, that means that on average you'll get 50% loading per site, which means you'll have about 250 pairs loaded on a single attempt. But if we're willing to use rearrangement for loading, then we can load all 1,000 pairs. And there's kind of a trade-off there, right? One of the advantages of this approach is that you don't need to load. You don't need to do rearrangement if you don't want, right? Because you only need 200. You'll on average get 250 pairs, and they don't need to be next to each other. But if you want to get that larger size, you know, you can go ahead and do rearrangement and achieve that. Okay, thinking about errors a little bit, the overall teleported CNOT error is determined by the Bell state fidelity, the local CNOT gate fidelities, and the measurement fidelities. And in particular, the errors all sum. And so you have 2 times local gate errors plus 2 times measurement errors plus the Bell state fidelity or Bell state errors. So, you know, you're going to want to make sure that none of these things is vastly larger than any of the other ones. And I should add that this Bell state fidelity is itself going to include some measurement fidelity, right? Because this is a heralded Bell state. So the error of measurement is going to kind of also be in the Bell state error. However, because of our symmetrized protocol, you know, we are insensitive to a lot of things you'd be worried about otherwise. So for example, slow drifts in the coupling strength, slow drifts in the amplitude of the different lasers involved. We're insensitive to all of that because our whole protocol takes, you know, 10 microseconds, and we only need everything to be stable over that small window of time. Okay, so let's do a bit of a comparison then. So here's a comparison of our any-to-any connected system to a Rydberg array limited to nearest neighbor gates. So the average non-local CNOT fidelity, or I guess the error, the average non-local CNOT error increases with increasing system size, right? Because the only way to do a non-local CNOT with nearest neighbor gates is to do a chain of swaps all the way across. And in contrast, our direct non-local CNOT error is constant, independent of system size. Right now, as probably Ethan was alluding to, one drawback of our architecture is that even though it's not one-dimensional, it is inherently serial. Only one photon can be in the cavity at a time. And this could be a problem. Well, first of all, say this is not a problem if your qubits have an infinite lifetime. You know, things take longer, but you know, that's not, at least the first order, a big deal. But if your qubits do have a finite lifetime, then that's going to add to your gate errors essentially. So here's a plot where we consider the effect of the non-local gate speed on qubit storage errors in a serial any-to-any connected system. So here's our gate error, which is just a constant as a function of system size. However, we will have storage errors, and the idea is that if your non-local gate takes time t and your qubits have lifetime tau, then there's a probability of n times t over tau of a qubit storage error among any of your n qubits during your gate. And you know, the solution, of course, is to make your gate super fast. But you know, no matter how fast it is, there's always some point at which your system size is so large that being serial is just not a good idea anymore. And I mean, to summarize this whole plot, I would just say basically being serial limits your system to a maximum size set by the ratio of the lifetime of your qubits and the time it takes you to do your gate. But I want to add, though, that in a locally connected system, all those extra local swaps don't just increase overall gate error, they also have to be performed sequentially, right? One after the other. And so the, you know, totally local system is also serial. And doing a long range gate is going to involve, you know, more operations and also more time because they're happening serially. And that's going to lead to both increased gate errors and increased memory errors. In general, though, the time that's required to perform n non-local gates across n qubits depends on both the degree of connectivity and the degree of parallelizability. So here I've kind of got a plot where I'm showing this sort of two-dimensional thing of a lot of parallel versus serial, low connectivity versus high connectivity, and different architectures and kind of where they fall. You know, so a very, very long 1D chain of ions that are basically nearest neighbor connected but can sort of shuttle around would be an example of a very low connectivity but totally parallel system. our system is an example of a fairly serial system that's totally connected. And then, photonic interconnects, part of their appeal is that they're both highly connected and, at least, depending on how you implement the actual interconnect, also parallel. So if you to compare like a full serial and any architecture with a fully parallel and nearest neighbor in 1D, then this one has worse gate errors. And actually the storage errors are the same because swap gates are carried out sequentially. However, if you let this one become two-dimensional, so it's sort of somewhat connected now and fully parallel, now it'll only take a square root of the system size number of swaps to get all the way across. And I'll sort of summarize and say, as a general rule, local systems in finite dimensions, so something like this, requires increased amounts of parallelization to equal or exceed the storage error performance of a serial any-to-any system. And they always have worse gate errors. And I can't help but add that our architecture can also be extended to include multiple cavities, like I've drawn here, which would allow both larger system sizes, up to and exceeding 10,000 qubits, and a higher degree of parallelization. All right, with 1 minute left. In summary, I have described to you a new architecture for connecting Rydberg atoms, which turns out to apply also to connecting trapped ion chains using an optical cavity. Our architecture enables the scaling of quantum processors to much larger sizes, enables the scaling of totally connected quantum processors to much larger sizes than possible with currently proposed methods, unleashing highly connected systems with many hundreds or thousands of qubits for NISQ applications. We're excited about this, both in terms of the NISQ applications, but we're also really hopeful that the feasibility of larger, highly connected quantum devices or platforms will inspire further theoretical investigation into quantum error correcting codes, which take advantage of that higher degree of connectivity to improve things like coding efficiency or error suppression. And yeah, thanks very much.
Thank you, Josiah. And we're all clapping, even if most of us are muted, so you don't hear it, but trust me. So that was a fascinating talk. It's always exciting to see new proposals and ones that go both into the quantum computing side of it and also into some of the nuts and bolts details. Are there any more questions?
Yeah, I have one question. That I guess I didn't quite understood how the degeneracy between the or the non-degeneracy between the Rydberg states and the ground states are addressed here. Like you said that the shift is around like a couple of gigahertz, right? So, and if I remember, all your timescales are on the order of microseconds. So, like, doesn't that kill your coherence, or am I missing something?
Actually, I totally understand. So, like, let's say these hyperfine ground states are 6.8 gigahertz apart, and they have like effectively infinite lifetimes until you start worrying about like stray magnetic fields. And so, right, as long as you can resolve them, and that's easy because they're gigahertz apart, then you can, control which state you're in and do coherent operations. And yeah, I mean, so it could be that when I'm saying that they're 6 gigahertz apart, I mean like they're splitting, not their line width. So they're basically like, 20 millihertz wide. So that's the dephasing rate. And then they're separated by many, many gigahertz. Does that answer your question?
Maybe, but like what I was thinking about was more of the fact that like they have like the phase is going to be changing as time evolves, right? Like between like you have the first term plus the second term, but like there's a time associated like phase with that, right? Or maybe I'm just confused about something.
Well, let me just try to draw something. So so like we drew these, I don't even know why we drew them like this. So like these two guys, I would really just draw like this. It's basically your ideal two-level system. So we only drew them together just to make the figure like compressed.
Right, yeah.
Yeah, so like this, these aren't meant to be, these aren't meant to be like magnetic sublevels, which are coupled by like magnetic fields and are gonna be like rotating into each other. Like these are gonna be very well isolated for basically forever.
Well, I'm not worried about the de-excitation if that was what you thought I was asking. I was just like talking about like the addressing time needs to be like around the order of the energy separation, right? Like there's the phase evolution.
It couldn't be faster than that, but it's actually much slower than that. Right. You could do it in a fraction of a nanosecond because they're 6 gigahertz apart.
Right, and doesn't that? I guess that doesn't have to do with anything to do with like the transverse time between like the two atoms talking to each other.
Well, yeah, it is right that so we do everything on the sort of microsecond time scale,
right?
You know, which is sort of megahertz bandwidth, and we have like 10 gigahertz isolation.
Okay.
Yeah, we'll chat more later today. I'm happy to go into this more with you.
So, Josiah, I might have missed something. I want to come back to what I was trying to ask about before. You made your point about the number of sites, and that's all great. But maybe I missed a bit where you explained what you're assuming for the origin of this addressability. I was picturing something like Monica Schleyer-Smith's experiments where they use a gradient. Are you just presuming that we actually optically address all of these 10,000 sites independently and brushing? Okay.
The experiment is a 2-centimeter cavity and a tweezer array inside it, and a tweezer array allows us to load atoms in at least two-dimensional arbitrary configuration. Yeah. Right.
So purely technically difficult, but no fundamental issue with that. That's fine. David has a question, but cannot speak, interestingly enough. So I will read his question. And the rest of you, by the way, if you feel like typing in a question or raising your hand because you're not comfortable jumping in, go ahead and do that and I'll try to notice. But here is David. My understanding was that most interconnect proposals in which the entangling information is encoded in the presence of a photon are limited because fidelity of the state relies on the heralding, e.g. dark counts. It seems that in the cavity implementation, you may have gotten around that since the readout is different. Is something swept under the rug here?
Totally. Yeah, we do get around that because we do not need to detect a single photon ever. So by keeping everything inside the cavity, right, the photon just stays in the cavity and goes from one atom to another. And we just measure the state of an atom, and we can do that by either detecting many fluorescent photons or not, or by sending like a pulse with 100 photons into the cavity and looking at whether it's transmitted or not. So there's no single photon detection required. So we are like definitely protected against the usual fidelity limits on, like, if you look at like typical remote entanglement generation schemes, they involve like pairs of photons and doing like Bell state measurements on them. You got to detect 2 photons. And that's an inherently hard to do process with like, threshold level errors, which we don't need. Yeah, really good question.
Questions from others? Again, either jump in or raise a hand or type something as you wish.
I think I may have missed this during the presentation, but that's a good point for me to take away. So what is the advantage of using the Rydberg state compared to using excited states with lower N?
Totally. So once we have our entangled communication qubits, in order to enact a teleported quantum gate between the memory qubits at node A and node B, we have to be able to do a 2-qubit gate still. And that 2-qubit gate could be implemented in whatever your preferred method is, but we need a high fidelity 2-qubit gate. And so we're going to use Rydberg blockade to do the 2-qubit gate.
Okay, so it has to do with Rydberg blockade.
Yeah, yeah. We need the qubit. We need communication qubits and memory qubits at node A to be able to interact strongly.
Thank you.
I see Aaron.
Aaron does have his hand up, but before that, David's had a quick follow-up question. So let me start with that. Can you comment on the beta being the same for each of the two loss events?
Yeah. So in terms of things like, what if your stirrup pulses aren't identical? I think we're pretty confident that we can, to pretty high fidelity, do repeatable stirrups in 5 microseconds. Another big worry would be that like the atoms would move compared to the cavity, right? But typically the cavity is going to have kind of a kilohertz motion. It's not going to be this mechanical thing oscillating at megahertz, right? And so we think that we're safe from that as well. This was actually like a big concern for us on the trapped ion front. So in the trapped ion version of this implementation, rather than a pair of Rydberg atoms, it's a trapped ion chain with one of the trapped ions on the end of the chain in the cavity and the rest not. And you're using Coulomb gates, which means you're using like the motion of the ions in the chain to do the local operations between the communication and memory qubits. And that means that there's like a lot of residual motion for that version. So if I go back to my very first slide where I had this, you can see in the ion version, we've got a chain, it's all lined up, and we're relying on, different modes of motion in each of those little chains. And if that end qubit is like wildly oscillating, then it will not be coupled to the cavity at every point in that oscillation, because it'll be going in and out of, an antinode or a node of the cavity. And this actually is like this limits our fidelity in the ion version to like 99%. So yeah, I mean, there's probably more to say about that, but it was a bigger concern for trapped ions because their motion is harder to deal with.
All right, Aaron?
Yeah, so I have a question. Maybe if you go back to your experimental implementation slide, I'm kind of wondering which parts of this have already been demonstrated. This, I mean, seems like a super complicated.
So in the theory version of the proposal, we kind of went all out, right? I will say, like, memory, ytterbium and rubidium arrays have been demonstrated.
Together?
No one's demonstrated like a ytterbium rubidium Rydberg gate yet. But I also would say that that's not really required for our proposal to work. It's just, I mean, you could replace ytterbium with rubidium-85, right? What's most important is that the communication memory qubits don't have like the exact same optical transition.
But then you're still saying in every node, you need 2 atoms, either an 87 or an 85, or maybe 2 different 87.
That's right. So you would need to be able to at least do like rubidium 85, 87 Rydberg gates. But that's not going to be a big concern, right? Their Rydberg levels are fairly close.
No, to me, the question is just creating a lattice where you know that every site has precisely one of each.
Yeah, I agree. That's an additional level of complication. I think even if that turns out to be hard, though, like I say, it's not very hard to make your qubits not talk to the lattice, or sorry, to the cavity. It would almost certainly like make it harder to pack all 1,000 in.
But so when you say it's not hard to make them not talk to the cavity, I mean, you have to make them not talk at all to the cavity, right? If they're very slightly, you have 1,000 atoms in there, each one has like a very small probability of absorbing a stray photon. It's not good.
No, that's true, and I think that's why we sort of say that ideally there will be a dual species experiment. I know that on the trapped ion front, there's been a lot of work on dual species chains, and I think it's just earlier days for Rydberg arrays.
Mm-hmm.
But given that these are like, reconfigurable platforms. It's not so hard to imagine loading an array with a bunch of rubidium and then loading an array with a bunch and then just like putting them together. Yeah.
I think when Josiah says to make an atom not talk to the cavity, he doesn't mean like put it in a node or pull it out of the cavity mode. He means put it in a state that's not resonant with 780. And that is indeed somewhat straightforward, at least for finite lengths of time. What I'm curious about is, since you acknowledge that, I wonder to what extent it really is even necessary to have two atoms, or whether you couldn't just put the atom in a different manifold of states, maybe not an alkaline, maybe an alkaline earth or something, where you share the entanglement. I guess the argument is you'd still want the information that's stored in the atom, and you want separately to create the Bell states. So you'd want each atom to contain 2 qubits, but maybe there's a way to do that. I mean, at a conceptual level, if you could generate entanglement among the nuclear spins and let the cavity, store the other information in the electron spins, might it not be easier just to have the right 4 states in a given atom?
Right, yeah. So if you can store 2 qubits in an atom, one in the location, electronic states that can interact with the cavity, and one in some other, well insulated.
Yeah. So people have done this with ion, or not demonstrated, have suggested or proposed this for ions, where you use you store use multiple levels to store the qubits. You can store an optical qubit, or you can store microwave qubit, or and so.
Right, but that wouldn't work for us, right? Because
it's
I'm
more challenging.
struggling to think of. I don't really know how to access anything except the electronic degrees of freedom of an atom.
No, right. And, it's not as though the nuclear and the electronic were isolated from one another. And if they were, it wouldn't help you. But if you think back to the Sirag-Zoller scheme, right, it all comes down to coupling 2 different kinds of systems. There, of course, it was motional. But I think as soon as you had 4 different levels that were all long-lived and that you could connect in the different ways you want, in principle, this kind of architecture would be possible. And I don't know whether that would be harder or easier than what you're proposing. It sort of moves everything onto the manipulation rather than into the creation of the lattice itself.
So my other question is, okay, so there is the two species, which is difficult, but there's also, and I just don't know what people have done, individually addressing multiple Rydberg atoms in an array, and doing 2 qubit gates between them. How much of that has been demonstrated?
That's coming online, I would say. So what's been demonstrated is large arrays with with individual single qubit gates, and then global 2 qubit gates. And that's enough to in theory do individual 2 qubit gates, right? Because you just sort of stark shift all the levels you don't, or all the atoms you don't want to participate in the global gate away. And I think there are experiments coming online that have full individual addressing.
And what's the numbers?
They would be smaller. So the biggest one is the Harvard Rydberg array. Then they have 250, and that's global. But they're building a Gen 2 apparatus right now, which will be bigger and will also have full individual addressing. So it just requires you to have both a 2D array for your 780 and a 2D array for your 480. Or at least that's the most brute force way to do it. So the main challenge is power constraints, basically, right? But I mean, part of the reason to go to a 480 array is that you can then focus your 480 beams down to a micron each, and that'll actually save your power, right? Versus trying to have some global beam that's hitting all of them.
Well, thank you. Does anyone have one last question before we let Josiah grab his lunch prior to his next set of meetings? If not, let's just all join in thanking Josiah one more time for a provocative talk. Great job, Josiah. And we'll be talking to you this afternoon. Have a
Looking
nice
forward to it.
afternoon, nice weekend, everyone. Bye-bye.
So if I just like leave this up, can I just go away and like come back? I guess I can just close this and jump back on the link at 1.
That's what I was thinking too. And I think I will leave myself, oops.